This video is going to be a lot more explanation of how our rockets work. Remember that in class we diagrammed our rocket in 3 phases of its flight. We called them the burn, when water is actually coming out of the rocket, so maybe it should be called the squirt. The second phase, the rocket has run out of water to squirt out, but it still has upward momentum. This is the coast. And then eventually gravity and drag win, and the rocket starts to come down. Then we have the descent. So let's take a look again at the forces acting on the rocket during those 3 phases. During the burn, we have the thrust pushing upward. This means that as the rocket pushes backward on the water pushes forward on the rocket. We call that thrust. It's an example of Newton's third law. We have gravity pulling down on both the rocket and the water inside the rocket. That's the weight. And we have drag pulling down, because when the rocket moves up, the air is pushing down on the rocket as the rocket cuts through the air. During the coast, there's no more thrust, so we still have weight and we have drag, but they're both acting to slow down the rocket as it moves up. During the descent, we have weight acting down and drag acting up. Now they're opposing each other, which means we have the potential for a terminal velocity, like we've seen earlier. Let's take a look at these forces in terms of just the coast and the descent to start. So we'll leave thrust out of it and just explain these. It is going to happen that sometimes these are in the same direction and sometimes in the opposite direction, but we can handle that easily in the code. So suppose we have Newton's second law. It says that the net force, the sum of the forces, is equal to the mass of an object times acceleration. So what is the sum of forces we're talking about here? Well, we have 2 forces, the drag and the weight. So drag plus weight gives me ma. A is the thing I'm really seeking, so let's rearrange this a little bit to say ma equals drag plus weight. We've just swapped the sides of the equation. And because I want a, I'm going to divide both sides by m. So acceleration is 1 over m times the drag plus the weight. These are both vectors, so they might be up or down. A is a vector too. What do we have in terms of expressions for these? Well, we've seen in a previous video that the expression for drag looks something like this, where k, buried in this k constant, we have a whole bunch of stuff. There's like a 1/2 density of the fluid times some drag coefficient CD times the area of the rocket. But we don't care about that today. We'll just call it k. The drag is proportional to the airspeed squared. And then this factor here ends up looking either like a sine or a cosine of the angle of inclination of the rocket. And we've calculated that in Scratch and in Python before. And then we have the weight. How can we account for weight? Well, fortunately, this is much simpler. The weight is just the mass of the rocket times the acceleration due to gravity. Over the heights that we're talking about, this acceleration due to gravity is going to be basically 9.8 like we're used to. So it's a constant. So we have these 2 forces equal to the acceleration. All we need to explain is that third force on the way up, and we'll have an explanation of everything. We'll be able to predict the acceleration as a function of time. That's what we really want if we want to write a code that lets us simulate rocket behavior. So let's add to these 2 forces. The third force, thrust. Again, we're taking every one of these forces and dividing by mass so that we have just the acceleration. So acceleration is thrust per mass plus drag per mass plus weight per mass. So what is thrust? Well, Newton's second law, as you usually see it, says the sum of the forces equals ma. But this is not exactly true, and it's not even what Newton wrote when he wrote the Principia. When he first laid out the statement of what is now called Newton's second law, he said not F equals ma, but the net force on an object is equal to the rate of change of its momentum, p. Now, to review what momentum is, it's simply the product of mass and velocity. So the total net force on an object is equal to the time rate of change, the rate at which this quantity is changing, mass times velocity. You might know that if mass and velocity both change, this can be a little bit more complicated. If mass were constant, this would just be, we could pull the mass through the operator here and just say the time rate of change of velocity, which is acceleration. So we just have ma. But in the rocket's case, mass is changing. So what do we need to do? In this case, we're applying a product rule because we're taking a derivative of a product of two functions where both functions are functions of time. Mass is a function of time because the rocket loses water. Velocity is a function of time because the thrust is changing as the pressure inside the rocket changes and we run out of water and it picks up speed, drag acts on it. So we have two functions of time. In that case, we need to take the first function times the second one's derivative plus the second function times the first one's derivative. So we have m dv dt plus v dm dt. Now see here we have the term that we're traditionally looking for, that ma, m dv dt. So we can just take this term, put it by itself on the other side, and then we'll have what we would normally call the net force plus this term over here, v dm dt. So when we rearrange those, what we see is that term is the thrust. We're moving it to the other side and identifying this v as the velocity of the fuel, of the water as it squirts out of the rocket. So thrust is the product of two things, the fuel's velocity and the rate at which the rocket is able to throw away mass. I could stand on the back of a truck and throw massive balls off the back of the truck, and as I exert a force backward on those massive objects, they will exert a force forward on me. That's what we know from Newton's third law. So this thrust can be made large in two ways. One is to throw the fuel, eject the fuel really quickly, and another is to lose a lot of mass per time. So it might be good to have dense fuel, and it's also good to get rid of that fuel as rapidly as possible. This thrust is the thing we're really interested in here, the thing we haven't dealt with before. We want to add this to our understanding of how the rocket behaves. Let's look at it in a little bit more detail. Suppose I have the rocket here. This is a crude depiction of our rocket. We've got a nose cone, we have a chamber, and we're going to fill that chamber partially with water. So in here we have air at some pressure, the pressure of the air, and we have some volume of air, VA. Now as the rocket moves, we have a nozzle on the end, water is going to squirt out, and what's going to happen to the pressure in the rocket and the volume of air? Well, the volume of air is going to increase, and when we increase volume of air, but it's trapped behind that water, the pressure is going to decrease. So if we graph that, we have pressure as a function of volume. When the volume grows, the pressure will decrease, something like this. And we're not sure yet exactly what that function is, but we will see what it is shortly, and we'll study it in quite a bit of detail this winter, later in the course. So we're losing the fuel, and as that happens, the thing that's causing the fuel to leave, the pressure inside the rocket, is dropping, but it's not dropping to zero. It's still higher than the pressure out here in the atmosphere. So we're still going to push this out, just less and less effectively as we push on it. So we get the biggest push at first, biggest pressure at least. So let's put that fuel back in the rocket and rotate it on its side to take a little bit closer look at what happens as we push on it. We're pushing the fluid out, so this is the amount of water that's been replaced by air as we push the fuel out of the rocket. So what is this shape going to look like when it comes through this narrow nozzle? Well, it's going to end up being a much longer, thinner tube of water you can picture, and we'll see in some video clips of our own rockets that this is basically what the rocket ejecta looks like early in the flight, very early. So how long is this thing? Well, if I want to know how many meters of water leave the rocket in a second, all I have to do is know the speed of the fuel as it moves out of the rocket. So the speed, which is the meters per second of fuel, we'll call it U, is going to be the length of this cylinder, and the cylinder's cross-sectional area will be just the area of this nozzle. We're calling this A, the nozzle area. So the volume of water ejected from the rocket will be the speed of the fuel times the cross-sectional area of the nozzle. We want to understand how to predict this volume as a function of time, and also how to predict how much mass we're losing per time, like we saw in our thrust equation. And that's simple, fortunately. The change in mass is just the density of the water times the change in volume. So if you can figure out volume leaving your rocket per time, you'll know the change in volume, dV, and you can just use that to multiply by the density of water, which is 1,000 kilograms per cubic meter, and that will give us the change in mass. So we want two things if we're going to have hope of really explaining this rocket behavior. The first is we want to know, how does pressure depend on volume? What we mean in there is, how does the pressure of this air trapped inside the rocket change as the volume of air increases and the volume of water decreases? And the second thing we want to know is, how do we find the speed, u here, how do we find the speed of water based on that pressure and volume inside the rocket? So what we'll take a look at next time in this rocket equation is, how can we calculate the thrust using the pressure inside the rocket? We need to know two things: how quickly does the fuel leave, and how quickly are we losing the mass? Check that out in the next video.